Hey guys, we made it. We are on our last chapter that we have to go over before you take your online AP exam, May 22nd. Mark your calendars. Before we get started, I kind of want to tell you a few things and have you grab a few things before you get into the lesson. As you can see, we're going to be really digging into the formula sheet. We are also going to be using a calculator. You're going to want a calculator. I'm also going to be referring a lot to your textbook because I'm having to go back to kind of old school giving notes because our stats medic activities for unit 10 or chapter 10, they weren't very feasible to do virtually. So I'm going to just go back to the old way of doing it. So the notes are in your Google Classroom if you want to print those and take notes as we go. So grab your book, your textbook. Oh, I said that twice. Grab your textbook, grab your formula sheet, grab a calculator, and if you've printed out the notes, grab those. And when you have all that, come on back. Okay, chapter 10 is going to be about comparing two proportions. We're going to be doing confidence intervals and test of significance when we're dealing with two populations. So in other words, like if we were going to compare a parameter of men versus a parameter of women, or if we ran an experiment, our first population would be the people who took the active drug, and the second population would be the people that took the placebo. So these inference methods are some of the most common that you will see in the world of statistics. So before we can get into test of significance and confidence intervals for two proportions, we need to talk about what the sampling distribution of the difference between the two proportions is going to look like. And in a few minutes, it'll be clear why we are subtracting. But bear with me, we'll get to that. All right, so at the top of page 605 in your textbook, there is a picture of the sampling distribution. If you want to have a visual, go over there and look at that. It's the third graph. The sampling distribution's technical definition, as we've seen before, is going to describe all the possible values of these differences and how often they occur. And of course, to do our test of significance and our confidence intervals, we need to understand what the shape, center, and spread of this sampling distribution is and any conditions that we need to meet. So I have taken a picture of page 606, the yellow box. So here are the shape, center, and spread for your sampling distribution of the difference of two proportions. All right, so if you read the shape one, it is very similar to what we did in the last two chapters. In the last two chapters, we just took the sample size times the proportion and then the sample size times 1 minus the proportion. And we had to make sure that those were at least 10. Well, this time we're going to do the exact same thing, but we have to do it for both samples. So you will find the sample size times the number of successes for both samples. You'll find this sample size times the number of failures for both samples, and you'll need to check that they are all at least 10. And if that's true, then we have an approximately normal shape, which is important because then we'll be able to find p-values and such. The center is going to be P1 minus P2, just the actual difference in the sample proportions, because it's going to be unbiased. And we learned that that means that the center of the sampling distribution would be the center of the population's distribution. The spread is that lovely formula there. And this formula is provided for you on your formula sheet. So I'm going to go over there now. I'm going to scroll down. So your parameters for your sampling distribution for two populations. Where did it go? There it went. For proportions, there is the formula that I just showed you. So you don't have to worry about memorizing it or remembering it. You just need to know where to find it. And okay, we do have a condition here, of course, the 10% conditions. This is what verifies independence for us. All right. Now there is a little different thing we need to talk about. The pooled or combined sample proportion and why we're going to have to pool proportions. So the But before we get into that, let's remind you about your setting up a significance test. So your null hypothesis for your significance test for the difference in two proportions. What we were going to start with is that our first proportion is going to equal our second proportion. And that means there is no difference between like the percent of men who like blah, blah, blah versus the percent of women. And this is going to show you why we are subtracting. So if we think about algebra for a second, oops, that should be an O. I'm going to subtract P2 from the right-hand side. So P1 minus P2 is going to equal 0. So then that's why we are looking at the sampling distribution of the difference in the two proportions. So you can write your null hypothesis in either of these two ways. You can put P1 is equal to P2, or you can put P1 minus P2 is equal to 0. Okay, so then your alternative hypothesis is going to be that our first proportion is either going to be greater than, less than, or not equal to our second proportion. So if you wrote that using the difference, man, that looks really confusing. Let's just put kind of some, that didn't work. Well, just rewind it if you want to know what that means. So if I subtract P2 over, so you're going to have P1 minus P2 is going to be greater than, less than, or not equal to 0. So that's a quick review on writing your null and your alternative hypothesis. Remember, we're looking for evidence in favor of the alternative hypothesis. And that evidence comes in the form of a p-value. But there is a little something different because we are obviously working with two proportions instead of just one. And we need to learn about what something that's called the pooled sample proportion. So pooling means we're going to combine the two population proportions. So your p hat, and I'm going to use C for combined. You can see why we don't use the P because we've got pooled, proportion, p-value. We already have too many P's. So we're going to do p hat sub C. And basically you're just going to add your results, your successes, if you will, and you're going to add those together and put in the top, and then you're going to add your sample size and put in the top. So this top number right here, this is your combined successes. Man, that is horrible. Look at that. I hope y'all haven't forgotten I'm a horrible speller. Combined successes. And this is over your total number of subjects or people or whatever you're doing. So the total number of people that you've asked the question of or the people in your experiment. So let's look at your formula sheet and see what they have here. Okay, so right here, you see what I just wrote down. You see p hat sub C is equal to x of 1 plus x of 2 divided by n1 plus n2. So that formula sheet is there. What I just wrote down here is on your formula sheet. Look. All right, so why do we pool? We're going to pool when, let's change colors so we can see a distinction. We pool when we are going to assume P1 is going to equal P2, which as you can look right above, that is your null hypothesis up here. So when we're doing a significance test, we will pool our sample proportions because we will be assuming that P1 is going to equal P2. And basically the reason we pool is because when you combine your successes and you combine the total number of people in your sample size or things in your sample size, we get a better estimation of a p-value because as we've learned before, more information is better. So we will pool our sample proportion when we are running our test of significance. So what is the test statistic for a test of significance? You got it, it's Z. So I want to go back to your formula sheet and remind you that your test statistic is right here. So that is all you're given in terms of how to calculate a test statistic on your formula sheet. You're given this in words because then you can apply the correct symbols based on the type of test that you are performing. So using those words, our test statistic is going to be Z, so we're dealing with proportions, and it's going to equal your parameter. Well, the parameter of interest is P hat 1 minus P hat 2. Our sample proportions. We're going to subtract the sample proportions minus 0. Now, where does the 0 come from? Go back up here. This is your parameter right there. So when P1 minus P2 is equal to 0, remember our null hypothesis is always written using our parameters. So that's why we put 0 in for our parameter. So test statistic equals the statistic, so the numbers we get from the sample, subtract, find those differences, minus 0, because that is our parameter value based on our null hypothesis, divided by the standard deviation of the statistic. Well, that is going to be where we use the pooled statistic. So I'm going back to your formula sheet. What do you see right here? When P1 is equal to P2, I guess I circled the wrong one first. When P1 is equal to P2, we have our standard deviation of our statistic. This is the denominator of the how you find your test statistic. Now, I want you to compare this top formula where I have the samples right here to what we just did. To what's typed right there. And you've got a choice to make here. You can trust that when P1 is equal to P2, the standard error is, or the standard deviation is given by this formula down below. And it is basically this top formula rewritten using the pooled sample size. So you can trust and use this formula, or you can take the formula that I have this arrow pointed to right here and just change all of those P's, P hats to P sub C's. So I'm going to come over here and write the one that matches the formula that is on the formula sheet. So it's going to be P hat C times 1 minus P hat C over N1 plus P hat C times 1 minus P hat C over N2. Now, remember, there are two different ways you could use that formula. You can use this one, or you can use what is circled in blue. What is circled in red. Those are the exact same formulas. The issue is if you want to use the formula that I have the red arrow pointing to, then you need to remember to change all of those 1s and 2s to the letter C, like I did here. All right, what are the conditions for conducting a 2-sample Z test for a difference in proportions, and how are they different from a 1-sample test? Okay, so the conditions, of course, is we must have random. We must have the normal condition be met and the independent condition be met. So that is basically the same thing we've been doing, just a couple little tweaks. Having a simple random sample isn't necessary if an experiment has been conducted. So do you see where number 1 says the data are produced by a random sample or, right here, or by 2 groups in a randomized experiment, which we're going to do a problem in just a minute with that. So whenever you are checking the random condition, you need to make sure you're using the correct part of this condition. Either the 2 samples were simple random samples, or the groups were randomly assigned. All right, normal condition, the counts of successes and failures are all at least 10. Your independent condition, which is your 10% condition, it says both the samples or groups themselves and the individual observations in each sample or group are independent. When sampling without replacement, check that the 2 populations are at least 10 times as large as the corresponding samples. That is your 10% condition. And there's some tweaks we have to make with this independent condition based on the way that what the problem is asking us for, and we will make sure I get into that as we go. So bullet number 2, the independent condition may not always need the 10% condition to be checked, and usually this will happen in experiments. And then, of course, check the normal condition for both samples. Okay, so let's do a problem. Are teenagers going deaf? In a study of 3,000 randomly selected teenagers in 1988 to 1994, wow, it's pretty old data there, 15% showed hearing loss. In a similar study of 1,800 teenagers, 19.5% showed some hearing loss. So it appears, based on this data, that hearing loss has increased in teenagers more recently than back in my day, 1988 to 1994. I was in high school right in the middle of that time. So, is this statistically significant? Do these data give convincing evidence that the proportion of all teens with hearing loss has increased? Well, I think if you take a second, process what the question's asking, you can see that there are 2 separate samples at play here. We have a sample of teenagers that are my age, and then we have a sample of teenagers from the early 2000s. This is how we know we have a 2 sample test. Okay, so as we do with all tests, we have to do the 4 steps. So we have to state. All right, so in our state step, we need to define our parameters. P1 is going to be the true proportion of all teens with hearing loss. '88 to '94. And P sub 2 is going to be the true proportion. I'm going to abbreviate, of all teens with hearing loss from 2005 to 2006. Now, I am doing this for the sake of time. You know, on your AP exam, you're going to write all that out. Do your null hypothesis. Your null hypothesis is that these 2 proportions are equal, so they have not changed. And of course, we can write that as the null hypothesis, P1 minus P2 is equal to 0. And then our alternative hypothesis is we think that the second proportion is higher. You see the word increased at the end of the question? So we think P1 is actually going to be less than P2. So our original proportion percent of hearing loss was smaller than the second proportions. And of course, we can write that P1 minus P2 is greater than 0. Both of these as a set are acceptable. So you could write the null and the alternative the first way without the number 0, but just be sure you're consistent. Or you can write the null and alternative the second way. Just pick one way and go with it. They're both correct. It didn't give me an alpha level, so as we've talked about before, we're going to put 0.05 as our alpha level. Okay, so we have our state step. So I don't have to keep scrolling. I'm going to write P hat 1 from our first proportion was 15%, and P hat 2 from our second proportion was 19.5. Our first sample size was 3,000, and our second sample size was 1,800. So that's just so I don't have to keep scrolling for a few minutes. All right, let's do our plan step, which says we are to check our conditions and name our test. So we are doing a 2-sample. Here's the name of the test of significance. A 2-sample z-test for proportions. All right, random. So the 2 samples were selected at random. So both samples, we did a simple random sample check. Normal. So we're going to check the counts of successes and failures. So I'm going to do, for the first one, 0.15 times 3,000, 0.15, 1 minus 0.15 times 3,000, and then do the same thing with the second proportion. I guess I should have done 1,800 times 0.195, and then 1,800 times 1 minus 0.195. So if you grab your calculator, I'm going to get those numbers. So 15% of 3,000, there's a decimal there, is equal to 450. And this is going to equal 2,500. Wait, that's not right. 3,000 times 0.85, 2,550. And then that top number is going to equal, when you do 1,800 times 195 is 351, and 1,800 times 1 minus 19.5% is 1,449, all greater than 10. So the normal condition has been checked. So independence. We were sampling without replacement, so we do need to check our 10% condition. So I had to look back at the numbers. It's 3,000 less than or equal to 1/10 of all teens from 88 to 94, and 3,000 less than or equal to 1/10, not 3,000, that's 1,800. 1/10 of all teens in 05, 06. I think that's pretty safe to assume, so we'll say check. But the other difference is, I'm going to scroll back up, is that, do you see right here where it says both samples or groups themselves and the individual observations are independent? So what we just did was we just checked the independence for the individual observations. So the other thing you have to ask yourself for independence is are these 2 samples independent of each other? So, these groups, groups are independent of each other. I'm really embarrassed by how gross that handwriting is, but it is what it is. Okay, so I need to give myself some more room, which of course is why I am doing this on Word. I'll pause this for just a second. Okay, do. What you doing here? Do. So our do step. First thing we need to find is our pooled proportion. So we're going to add our number of successes, which we found when we were checking to see that the number of successes were greater than 10. So 450 plus 351 over the first sample size, 3,000, plus the second sample size, 1,800. When you put that in your calculator, you get 0.167. So our z-test statistic is 0.15 minus 0.195. That is our statistic minus the parameter, which is 0, over the standard deviation of the statistic. So we're going to take our pooled proportion, 0.167, times 1 minus 0.167, divide that by our first sample size. And remember, we always add with standard deviations. So then we're going to do 0.167 times 1 minus 0.167 divided by 1,800. If you want to pause your video and see if you can get what I get, that would be glorious. I got -4. That's a 4, -4.04. So we need to find the probability that this z-score is, go back to your old, oh wait, what you doing? I don't know what's going on. Anyway, I guess if you go back up to your alternative, which I can't seem to make it happen, we were saying that it was less than our first proportions. Our first proportion from our first sample was less than the second one. So we're going to find the probability z is less than -4.04. So if you remember, what in the world is going on? Oh, I don't know. So if we draw that, wow, that's way too big. Oh, and it's on the wrong side too. Man, technology got me all messed up in the head. Let's try this again. So we're going to draw our normal distribution curve, -4.04. I think if you go ahead and think about your empirical rule, that means that we are 4 standard deviations below the mean. And we should know that that probability is basically 0. To find that probability, remember how you'll use your calculator to do that, or you can use your table, but you don't have to write down, because you wrote down the formula with the values filled in, you don't have to write down your calculator steps. You don't have to do all that, because quite frankly, you don't even have to touch your calculator if you remember what a z value means. That since this is, and you got to know the empirical rule. So since -4.04 is way outside of 3 standard deviations from the mean, remember 99.7% of the data is within 3 standard deviations of the mean, we know that this probability is basically 0. So then our final step is to conclude. And we're going to conclude the exact same way we concluded in the last chapter. Since the p-value is less than alpha, we will reject our null hypothesis. All right, so where in the world did all these letters go? So since our p-value is less than alpha, we will reject our null. We have convincing evidence in support of the alternative. But remember, we always want to put this in context. So we can't just say we have convincing evidence that the alternative is true, but we have convincing evidence that the proportion of all teens, remember you can go back and look at your problem and use the verbiage that they used if you need help creating a sentence, that the proportion of all teens with hearing loss has increased. Since 84 to 94. Whoops. Sorry about that. I didn't want you to have to hear me coughing. Unlike class, I can pause the video and do my thing and y'all don't have to bear witness. Anyway, so since our p-value was less than alpha, we had convincing evidence that hearing loss has definitely increased. And we could go into all the whys, but my suspicion it has to do with earbuds. Between the two studies, Apple introduced the iPod. If the results of the test are statistically significant, which they are, can we blame iPods for the increased hearing loss in teenagers? What you think? It's always a good time to think back, and the answer is no. When is the only time we can establish cause and effect? You need to have an experiment. So, no experiment was done. So, no experiment was conducted. So, cause and effect cannot be established. So, this is going to lead us into our next topic of discussion, which is doing a significance test on an experiment. And I realize this video is a little longer than normal, so if you want to pause, take a break, this would be a good time to do that. But I'm going to keep going. So when we are doing parameters, when we're discussing an experiment, students a lot of times in their state step, when you have to define your parameters, students will often use language that refers to the sample data, the statistics, instead of the parameters from the population. So one thing that is one way to incorrectly define your parameters, the proportion who took or the proportion of the people in the group, you need to make sure your parameters are addressing the population in general, not just the sample. So by using present tense, that will definitely help you avoid that mistake. And when we set up this next problem, I'm going to show you how to do it properly. So, drum roll. All of this stuff we have been doing, all of the math that we have been doing, please don't hate me, can be done in your calculator. So when I do the 4-step process on this next problem, I'm going to use this to show you how to deal with a test of significance for experiments. And I'm also going to show you how to utilize your calculator for the do step. And I will also discuss the drawbacks that are going to happen on the AP exam that you would need to be very careful of. So there'll be a lot of AP exam tips in here, because once you see how to do it on your calculator, you're not going to want to do it any other way. And you will be perfectly fine as long as you heed my warnings. All right, so in an effort to reduce healthcare costs, General Motors sponsored a study to help employees stop smoking. In the study, half of the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to stop smoking. None of the 878 volunteers knew that there was a financial incentive when they signed up. At the end of 1 year, 15% of those in the financial rewards group had quit smoking, while only 5% in the traditional group had quit smoking. Do the results of this study give convincing evidence that a financial incentive helps people quit smoking? These data came from a newspaper in Arizona. All right, state. I'm not going to write out state because you can see I need more room. So let's start with defining our parameters. P1 is going to be, let's see, we want to, what do these numbers represent? 15% of those quit studies. So maybe the true quitting rate or the true proportion All right, so do you want to let this P1 be the true proportion of those who had a financial incentive or those who did not have? Okay, I asked that question because I know you can't answer me, but I asked that question so you know that it really doesn't matter, but this is why you have to define your parameters. Your AP reader, me, we need to know what your P1 and P2 stand for, and the only way to do that is to tell us. So we want the true proportion of those who have financial incentive. And P2, the true proportion of those who do not have financial incentive. Okay, so I think I have enough room. So our null hypothesis is going to be P1 is equal to P2. And our alternative, I like using it like this because we can write it with the subtraction, but I like this better because it actually kind of shows you what you're investigating, that these two proportions stayed the same, or that the financial group had a higher rate of people quitting. So remember, P1 is the financial group, and that's going to be higher than P2. And we're going to let alpha equal 0.05 because it didn't tell us. All right, let's check our conditions. Random. Okay, so this is an experiment. So you better not say use the language of a simple random sample was taken. So in random, you need to say treatments were randomly assigned. So random assignment of treatments. So you would make sure don't use any super random sample discussion there. Independent. All right. Your 10% condition does not apply here. We were not sampling from a large population, and we didn't grab the people at random. So as with most experiments that we talked about back in chapter 4, your experiments subjects, they're going to be volunteers. People have to volunteer for an experiment. It's the randomization of the treatments that make it statistically sound. So when we look at independence, we need to decide the two things. Are the individual observations independent of each other? And I'm going to assume, and I think this is a pretty safe assumption, I'm going to assume the people who are deciding to quit are independent of each other. I mean, if your neighbor decides to quit, that probably doesn't have any bearing on whether their coworker decides to quit. So we're going to assume people decide to quit independently. And random assignment of treatments random assignment of treatments pretty much ensures that the results are independent. So your individual outcomes are independent. Okay, so I'm going to read that again. That's horribly. Gosh, my handwriting. Anyway. So when you're checking the independence condition for experiments, again, remember independence, we have to be checking two things. We have to check that the two groups are independent of each other and that the individual observations inside of those two samples are independent of each other. So people are going to decide, so the two groups or the volunteers for the experiment, they are deciding to quit independently of other people. We have to make that assumption. I mean, we know that in reality, if like a husband and a wife decide to quit, they're doing it for each other. But in general, we're going to make the assumption that people are going to decide to quit independently. So that's the two separate groups are independent of each other. And then the random assignment of treatments, we're going to make the individual outcomes of the treatments independent of each other. So always check with two samples. You have to check two things for independence. All right, let's check our normal condition. So we're going to take the 439. That was our sample size for the first half. Because it said 878 volunteers. So I took that in half, and that's where I got 439. So 15% quit in the first group. That's 65.85. 439. So 15% quit, 85 did not. That's 373.15. And then the second sample was 439 also. Then the second sample, 5% quit, so that's 21.95. And then we have, so 5% quit, 95 did not. Obviously, that's going to be bigger than 21, 417.05. So all of these larger than 10. So our normal condition has been met. Our independence condition has been met. Okay. So in our do step, so let's talk about the do step and the calculator. If you're going to use the calculator to do the do step, you have to 100% have to name the test. I have been trying to train you to name the method of inference in the last two chapters. So when you were doing a one sample confidence interval, you wrote one sample confidence interval for means, one sample confidence interval for proportions, and so on. If you're going to use the calculator to do the do step, it is imperative that you name the test or the method of inference that you're using. Otherwise, there is no partial credit or no consideration is going to be given. They're going to think that you pulled this number out of the air, or you copied it from somebody's paper or something. So in absence of the formulas, in absence of writing in and plugging in the values, the name of the test is crucial. So this is a two sample z-test for proportions. So if you do that, then you don't have to show any work. What you do have to show is your test statistic. You have to show your p-value. And you have to show your pooled standard deviation. Oh, I'm sorry, your pool proportions. Okay, so let's go to our calculator. Some of you may have found this neat little trick out in the last chapter, but I didn't want to show you officially because I wanted you to understand the inner workings of a test of significance. Your AP exam, since it's now online, they have said that you cannot, or no, they have said that they're going to create the problems in such a way that you do not have to have a calculator. So that makes me believe that you will not need to do any do steps. But what you would have to do would be to set up a do step using the formulas. So that's why I'm still going over these formulas with you. I have a suspicion that they will say something along the lines of, okay, here's this problem about quitting smoking. You're going to do the 4 steps, but they're going to give you the p-value because to be equitable among people that don't have the same resources as others, they can't make people do the do step because they might not have the ability to without having a calculator. So for your AP exam, because it's online, I suspect that they will say, set up the do step, but don't perform the calculations. And then they'll say the p-value is blah, 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 and then you'll have to do your conclusion. Okay, so I hope you didn't use this little trick in the last chapter, or you're going to struggle setting up those formulas. If you press the stat key, do you see the word tests right here? So go over to your test. There's your one sample z-test, number 1. So that's your one sample z-test for proportions. Number 2 is your one sample t-test for means. So today we're doing a 2 sample z-test for proportions. So we're going to click number 3. Now you have 2 choices. Do we have the data or do we have the statistics? So in this problem, we have the statistics. So make sure you go over and highlight statistics. All right. Oh, wait, that's not proportions. Stat, over to test. That was for means. We'll do those in a different video. We're going to do number 5. I mean, clearly it says prop for proportion. So we're going to do a 2 proportion, number 6. We're going to do a 2 proportion z-test. Okay, so x1 was, okay, so that's the number of successes. Well, in this problem, our number of successes was a decimal. Do you see our number of successes was right here, 65.85. Well, you're not able to put decimals in here, so you want to round according to your rounding rules. So your successes were 66. Your sample size for the first group was 439. All right, x2 is our successes for the second group, 21.95. So we're going to round that to 22. And we have 439 here. And our alternative hypothesis was saying that it was, where did it go? Greater than. So I'm going to highlight greater than. Press enter. I'm going to press calculate and get the p-value. But I want you to notice right here, do you see where it says draw? It will draw it for you. And right here is your z-score, your test statistic, 4.9. And your p-value is basically 0. So I'm going to do this again. Stat over to test number 6. It saves everything, so I didn't have to worry about that. The reason why you want to calculate and not just use the draw is it gives you the pooled proportion. So here is your z-test statistic, 4.94. So your z is, 4.94. Your p-value is basically 0. Can you see it really tiny right there? It's 0.1, 2, 3, 4, 5, 6. So it's 3.8 times 10 to the negative 7. So it's 6 zeros and a 4, which is basically 0. And then your pooled proportion is that very last one. Because see, that's your proportion for the first sample or the first group. That's your proportion for the second group. And then P with no subscript, that is your pooled proportion. So 0.1. All right. So since our p-value is less than alpha, we will reject the null. We have convincing evidence that a financial incentive helps people quit smoking. Okay, sorry that was kind of long, but it is there. And I hope you are good. Please come see me in office hours if you have any questions.